Welcome to the Zoomtown experiment, where anything that can go wrong certainly does, as we've witnessed in the past few months. Well, in reality right now, things are progressing forward very nicely. This video and the one coming up next, I'll be talking about all the maneuvers, the way the Zoomie moves around in Zoomtown, and then all the testing and results of the testing based on all the changes that I've done in the last month or so, I believe. Good news is things are actually moving forward with very predictable results. Testing has been good. I'll go into much more of that in detail in the next video. For today's video, I want to explain how the Zoomies are kind of moving along the way or the road surfaces through Zoomtown to get from point A to point B. I had done a video very similar to this probably about a year ago, but so much has changed in how I handle the logic of getting the Zoomie from A to B. And it's all been part of this most recent effort I'm referring to as the simplification process. So here's what we're going to cover. I'll be talking about the cruise maneuver, which is basically driving in a straight line from point A to point B. A pivot turn, which actually is almost two separate maneuvers, because as we make a sharp turn to pull into a driveway, or after we back out of a driveway, we would make a sharp turn to align with the next road. The behaviors are very different, but they're all encapsulated in one function. So that one's a little tricky to explain. The sweep turn is for the large radiuses at the far corners or far extreme corners of Zoomtown. We'll do the park maneuver, which gets the Zoomie parked in the driveway, unpark, which backs the Zoomie out of the driveway and gets it lined up to get back on road again. And then the final maneuver that's still in the code is called a pull-up maneuver. And right now I'm potentially eliminating that particular maneuver. I'm getting cruise, I've been modifying cruise and some of the markings on the road surfaces so that cruise can handle that particular motion. It's not really a big deal, but it's part of simplification. If I can have cruise do the work of the normal straight driving plus these special moves, why have a special routine to do the pull-up maneuver? To get you familiar with what that maneuver does, it's kind of unique in that with this, we're coming down this road. This is where the Zoomie will stop, at this mark, and that keeps the nose of the Zoomie out of the traffic lane. When the Zoomie needs to make a turn going right, it has to come up to this point, pivot, and go. Or if it's going to make a left turn, it'll come all the way up to this point, pivot, and then move on. Well, to get from this position, where it's safely back out of the traffic lane, to either this move or this move, that's what I'm calling a pull-up maneuver, just as you would when you're driving a real car. You would stop at the stop sign and then kind of pull forward before you aggressively pursue your turn, especially in the case of a left turn. So that particular maneuver, I think I'm eliminating, but I'll leave it in the code. And by the way, if I remember, I'm going to post this version of the code up there. It's slightly modified from the actual version just to add a little bit more spacing between lines to help me explain it. But I'll post this code so that you guys can go through and kind of try to figure it out along with me. For each of those maneuvers, I will demonstrate the maneuver. I'll have the Zoomie actually perform the demonstration. Then we'll go through a top-level explanation where I'm explaining what's really happening, just at a top level, no code. And then finally, I will then take you into the code and just show you block sections of each function so that you understand which areas I'm performing which particular operation within any maneuver. The first maneuver we're going to talk about is the cruise maneuver. The cruise maneuver drives in a straight line and will stop or slow down at a certain points along the way. But its purpose is to get from where it is and go to point B, the next position, in a straight line. The command line for that, which is the trip plan instructions, it's kind of like a mini program that I'm running, tells the Zoomy control program what motion I want to do and the parameters for it to be able to do that. It'll start out, I just put it into a variable for easy reading. It's a cruise, CRS. This is the absolute position of both X and Y, X being left and right on your screen when you look at Zoomtown, and Y being up and down, just as you would normally have, with the origin, the 0 point of Zoomtown being in the upper left-hand corner. This parameter specifies the distance to travel for certain moves. Primarily right now it's restricted to park and unpark. This parameter here is not needed. It's for deciding which way to turn, left or right. This parameter is for forward motion. W is the heading that the Zoomy is moving in. Cruise velocity is a variable that I'm using to specify the velocity, maximum velocity for which I want this maneuver to occur. STP is currently an unused parameter, but it will be incorporated, I believe, as I start to integrate with the scheduler software. And finally, this last parameter, which has no application here, would be the radius for a sweep turn. But this is the command we're going to execute to show you a cruise maneuver. While we're waiting for the code to get there, we're going to move from this point over to this location. And what we'll do is we'll detect that line and stop just as we transition off of that marker. You will notice that it slowly accelerated, got up to speed, maintained speed, and then slowly decelerated. Now, in certain cases, we wouldn't even decelerate to a stop. We would just continue moving through. Let's take a quick look at the input or feedback systems that allow us to make that maneuver. I'm using the encoders which are on the motors to provide positional feedback. I use the TCRT 5000 analog sensors, the two ones that are at the front, they're photosensors, to provide feedback for steering. As it moves along that guideline, it has to constantly try to keep itself centered on it. I also use the TCRT 5000s to provide feedback for the endpoint. That's when it will detect that black marker tape, and as soon as it transitions off of that marker tape, that is the exact point where I want it to stop. And finally, not necessarily an input, but the output for controlling velocity is using PWM, and I have to calculate a duty cycle to provide that velocity control. This is a top-level explanation of that motion. We will perform an acceleration at the start of the maneuver, and it will bring it up to the desired speed. And that's very tricky with cruise because sometimes I come to a complete stop, sometimes I want to continue at a specific speed, other times I'm starting from a dead stop, and sometimes I'm starting while already moving. That became a very tricky routine or code block to come up with. I will perform line following to steer the Zoomy, and that's using the two front photoreflective sensors. I'll perform deceleration near the end of the maneuver, and those both are detected and controlled by how far the Zoomy has traveled to determine when to stop accelerating or when it should be fully accelerated by, and then same thing in reverse for decel. It will stop a motion if the T off, that is my flag that I use for when it knows that it transitioned beyond a marker tape right at that moment. When it sees that and the encoder position is within an acceptable range, it will then stop. If it's not within an acceptable range, that's how I can differentiate from all the unrelated marker tapes. And that acceptable range right now, I believe, is 1/2 of an inch, or 13 millimeters. At the end of the maneuver, or near the end, if it doesn't stop and it keeps going because it couldn't see that marker tape, it will consider that it's a failed trip and it will abort the maneuver. And actually, at this point, it's crashing the program intentionally for a full shutoff with a 1/0 command so that it forces a total shutdown. I needed that more so, I'm hoping, only in testing, but the code will stay in there for a while longer. Hopefully I no longer need it and it performs properly. Coming up to the function perform cruising, this gets run continuously and it updates every single time, and the main loop right now is restricted to, I think, 5 milliseconds. So every 5 milliseconds this is going to get run. This first code block is all about getting the sensor readings from the two TCRT 5000s, and what we're trying to do with that is find a center point and move the Zoomy left and right during steering to maintain center line. And that's what all this code is to read the sensors, get the PID value that I want, the KP set, and then perform that function of steering. I have to then adjust velocity. I need to calculate a distance and then calculate a distance to go. This is the acceleration code, and you'll notice that I'm making a number of decisions based on how far it still has to go, the calculated distance of the overall length of this trip or this road. You'll see that's used numerous times depending on whether it's less than 3 inches, more than 3 inches, or greater than or equal to 2 inches, along with the distance to goes being less than 2 inches in a lot of cases, or greater than 2 inches. Each one of those conditions will greatly influence how the acceleration routine performs and acts. And there's a lot of variables that go into that, which made it so complicated. In this case, I'm detecting that T off, that's where I transitioned off the marker, and I'm within an allowable range of distance to go. If I'm less than 1/2 inch to go, plus or minus at that point, and I see that, I'm going to stop the motor and reset the whole system, update the position to say you are exactly at this particular location, which comes from that trip plan command line. Otherwise, we're just going to go through, update everything, and keep repeating this whole function loop time and time again. This code block here we'll see in other functions as well. It's saying if the distance to go is less than negative 0.65, meaning it went too far, at least in all its calculations, I'm going to stop the motor. I'm going to reset the trip plan executor, and I'm going to print out the positional data so I can analyze it. But then I fully abort the program by just commanding y equals 1 divided by x. It's an old school technique I've used for years, and I still use it here in Python. Now that'll wrap up the cruise function. I know I'm going through this really fast, but this could easily be a 3-hour-long video, so I'm trying to give you the gist of what the program is doing. So with that, let's move on to the sweep turn. The sweep turn, I specify that command with SWT, the ending X position, ending Y position, and I am providing the distance on that. Again, it's not important whether I'm turning left or right for this motion. Doing line following, I do have to specify that it's going forward. This is the ending heading when the movement ends. Here's the velocity in duty cycle that I want it to run at. And finally, the next motion should be a stop. Again, that variable isn't used. And this variable or parameter specifies the radius of the sweep turn. For this example, I'll start from the beginning. You'll see the Zoomy come to this point, pass through. You'll notice there's no marker tape to indicate the endpoint. For this small radius, this creates a lot of special conditions and problems. So I'm strictly working on distance traveled as reported by the encoders. Fairly straightforward movement, but one thing I want you to notice right now, and this will be important a little bit later, it's gone the correct distance, and if I had a marker tape up here, it would have stopped basically in the same point. But notice it's at an angle. It's not perfectly in line with the next road. That creates a lot of problems for using line following, and especially for the next maneuver. Well, we'll have a short cruise, but when I do the unpark maneuver and I come back out, I'm using the TCRT sensors on the back of the Zoomy, so if it backs up, it's going to try to back up on a turn, and that's not what I want. But that created several problems for me to resolve, and it's mostly done in the other functions such as pivot turn. We'll go back to our top level views, and we're looking at the sweep turn. The encoders on the motors are providing the positional feedback. The TCRT 5000 analog is providing, that means they're the front sensors. They provide feedback for steering, and the TCRT 5000 analogs provide feedback for endpoint, and that's on the large radius turn only. And you'll see that over here. If the Zoomy was coming from this direction, it would stop at the end of the line or end of the curve with a marker point, but that would not work for that tight radius over there. And again, PWM with a duty cycle is how we control velocity. Top level view, perform line following to steer, stop the motion as we transition off the marker tape, and if the encoder position is within acceptable range, or we stop the motion based on encoder feedback only on the small radius turn, and we stop and abort the maneuver if the encoders indicate we traveled past the expected stopping point. Moving on into the code, here's that very similar block of code for doing the calculations for line follow steering, just as we had in cruise. This is unique to this function. I have to, or what I'm trying to do here with this function is I want to plot the position along this turn and get that data over to the scheduler so that the animation there matches the physical motion here. And currently it's not working correctly, so I got to get back into that. That's most probably a problem on the other end, but that is the purpose of this code block. Here we're dealing with just about the whole business end of the sweep turn. It's got to make a decision if this is the small radius turn or the large radius turn, and then that changes the way it determines if it ends or how it ends. On the small radius turn, as I mentioned, I don't have a marker tape, so I work strictly on average distance traveled and then the distance that it needed to go. That's it. For the other one, where it's a large radius, I use the marker tape, so I look for the transition off and then for the average distance to be greater than 1 inch, meaning the next marker it should see is the end point. And that's it. So this particular routine is pretty simple. The other thing to be aware of with sweep turn, there's nothing that can happen from start to end of that as far as turning off of it. Furthermore, because of that, every road that ends at a sweep turn is going to just continue on at some velocity into the sweep turn all the way through it and continuing on to the next road without any need to stop. On to our next maneuver, we're going to do the pivot turn, which ends at 8.46 and y of 37 inches. And the distance it will travel in that pivot turn is 4.948 inches. It's making a right turn in the forward direction, it will end up going east at the end of it. This is the velocity for it. The next move, again, is unimportant at this time, and I do not need to specify a radius for a pivot turn. Now, once the pivot maneuver starts, everything goes pretty darn quickly with all the different stuff that has to happen. You'll notice it pivots on one wheel, rotates, and then it continues to rotate until the two TCRT 5000 sensors at the front of the Zoomy detect this white line, and it will stop as best as it can to be perfectly centered on it. At that point, it knows it's ready to move forward on the next motion. To do that, it's using the encoders on the motors for positional feedback like all other moves. The TCRT 5000 analog sensors, the ones at the front, provide feedback for the endpoint, just as I described a moment ago, for forward turning. And then the PWM function with a duty cycle is providing velocity control. The stop motion is based on that TCRT 5000 sensors indicating that the Zoomy is over the center line of the next road. And this is, oh, and I should include, and the encoder position is within range. That's very important. But this was an addition I did in this simplification process to make sure that I'm better aligned for, at the end of the pivot turn, to maneuver onto the next road surface, be it a driveway or a regular road. And that has been working pretty good. Hopefully I didn't jinx myself. We're also going to stop and abort this maneuver if the encoders indicate it traveled past the expected stopping point. And that's a really important thing. Again, it hopefully will never be needed once we get into actual running of the experiments later on. And I do make note that this has to handle special conditions at the destination number 4 and number 9, as when we're backing out of the driveway. That has no influence at this point right now. We'll get into the code, and this function is rather lengthy because there is so many things going on. We are going to go through, get a couple of variables set up, get a position established, read the sensors, and then I've got an offset in here, you'll notice at -1600, and that is to help keep the Zoomy either centered on the guideline or favoring the right side. That way I'm not going to get a slight head-on collision with the oncoming Zoomy as they pass by each other. This isn't fully implemented yet, and I really can't do much with that until all the Zoomies are running and tune it that way. Because this is a pivot turn, and depending on the direction, we have to make note of which distance I'm paying attention to, the right wheel or the left wheel. I cannot use average because average would cut literally the distance traveled in half. Then I have to determine if I'm going in reverse, meaning I'm backing out of a driveway in most applications. I have to use different data to determine for steering, and that's where I would get the digital photoreflective sensor states. Those are not analog values. They are just simply zeros and ones. So I check those, and then I go through and then check the steering and deal with it there. I have an else in here just because I needed to have a way to confirm this condition and not needed in the real code. This is the catch-all. If we did not see the center line and I'm 0.8 inches too far, I'm going to crash the program with this command, but I'll stop the motors first so that the Zoomy doesn't keep wandering off aimlessly. Now we're into the full breakdown of all the different conditions that it deems as an acceptable endpoint, and it has to do with whether I'm going forward or reverse, turning left or right, and dealing with the left line sensor, right line sensor, and the right offset so that I stay centered while steering, and the distance to go is less than 1/2 of an inch. And you'll notice there's slight changes to this, whether I'm turning left or right. This is left, this is right. Here it's got to be greater than 1,000, this one's got to be less than 1,000, etc. going through the code. That's a good stop, that's a good stop, that's a good stop. All the conditions that it would experience where it's doing what it's supposed to. And in this code here, we can see I'm handling the special conditions for destinations 4 and 29. This particular condition, or location, 90 for X, 10.32 is for the upper right-hand corner position 29. Diagonally opposite of that is destination number 4, which we see on the layout, is X of 6 inches and Y of 37.8. In either of these two conditions, it's going to have to do something differently so that we don't get trapped on that small radius curve. Going in a little deeper into it, here's where we're going to handle it. That is the generic condition to get us into this special area. And in here, when we reach that we're in the reverse mode and I'm turning right and the distance to go is less than negative 0.15, I will stop. Nothing to do at all with the photo state to detect the line sensor. In this condition, this is when we're moving reverse, turning right, but the photo state of the photoreflective sensors are saying I'm at a marker point, meaning I'm lining up on the center line, and the distance to go is less than or 1.35. So it can do this maneuver for all driveways except for destination 4 and destination 29. It's very involved. Pivot turns, that probably was the most complex maneuver to develop and get it to work in all conditions. The next most complicated thing was developing acceleration routine for the cruise maneuver. Those were the nightmares. With that, let's move on to the next maneuver. The next maneuver is park, PRK. It will end at this X, this Y location at the end of the driveway. The distance that'll have to be traveled is 3.29 inches. We don't turn left or right, but we are going forward, and in this case, I'll end up in the heading of easterly. This is the velocity. You'll notice this was a little higher than the pivot turns. Again, stop. This parameter isn't used at this time, and there is no radius to define. So that is the command line to perform the park maneuver. For parking, I'm going to use the encoders on the motors, just as I've always done. For positional feedback, I'm using the front analog TCR T5000s for feedback to determine endpoint. And PWM and with a duty cycle provides velocity control. At the start of it, I'm going to accelerate from that pivot turn and accelerate up to speed. I will stop the motion based on the TCR T5000 sensors from seeing the marker tape and in association with the encoder position being within an acceptable range. If it drove too far, we're going to get a system crash per my intention. It will decelerate near the end of the motion. I don't want to go too fast across those marker tapes. The faster I go, the greater the run-on is as everything slows down or decelerates to a stop. And finally, this is the note where we stop and abort if we go too far, and that creates a problem. Into the code for parking. We've got our basic line follow steering code at the beginning, setting all the parameters, etc. Update our positions, get a estimated to-go distance, and that's a special one we use in this function because of the constricted nature. We don't want to hit the barrier, so I wanted to have an extra or a different way of dealing with our stopping point, and that's what that guy's about. Here's our acceleration control. If I'm below 1.7 inches of travel thus far, I want the Zoomy to be at 0.6 override velocity, or 60%. And beyond 1.7 inches, I'll let it go at a full 100% velocity. Looking for the transition off that black tape, and if the estimated distance to go is less than 1 inch, it knows it's in the proper range and in the correct area to stop. And we'll see that here, motor stop, etc., and we terminate the motion. Otherwise, I'll look for the distance to go, and if it is less than 1.7 inches from the end of the move, I'm going to put the override value at 0.357. So that's just a factor. I multiply that times the velocity to have an override to decel to. You will notice that in several of these cases, you'll see me, I will not go all the way down to 0 on velocity, and I will never go all the way up to 100% on velocity, meaning with including the override and the programmed value. I need overhead on both ends to allow for steering. Plus, if you get too low, if I drop into that 0.25, 0.28 range, the Zoomy won't actually move anymore with the duty cycle being that low. So those conditions where I'm doing override have to have caps to their values. Moving on to our final maneuver, the unpark maneuver. That's abbreviated with UPK. We will end up at 8.46 inches and on X, 37 inches on Y. The distance to travel, 3.29 inches. We're not making a left or a right turn. We are working or moving in reverse, and we will be moving in the westerly heading. We will move at this duty cycle or this velocity, and we don't care about this parameter at this time, nor this parameter which specifies the radius of sweep turns. Let's take a look and see what this motion looks like. As it backs out, whether it's going to this road or to this road, it's going to back up and see that transition right here in that area. Once it moves past the guideline, it can easily detect whether it just crossed the nearest lane or the farthest lane. And in this case, you see it backed up and stopped precisely where I wanted it, at the far edge of the nearest lane. To do the unpark maneuver, just as with all the other ones, we're going to use the encoders to provide positional feedback, and then we will use the TCRT 5000 digital photoreflective sensors that are at the back side of the Zoomy for determining where the endpoint is. Obviously, this time it's not at a piece of black marker tape. We're detecting the light changes when it transitions across the next road's centerline or guideline markers. And finally, we use PWM to control velocity by adjusting the duty cycle for each of the movements. For steering, we're going to use the digital photoreflective sensors at the rear of the Zoomy, which provide us with just simply a 1 or a 0 as any digital signal. And based on that, we will adjust the speed of a wheel to accelerate as needed to steer the Zoomy. We'll adjust the velocities and or speeds and set the velocity. We will then check the steering again to get updated information. At the start of the motion, during acceleration, I'm restricting the velocity to 60% of maximum specified, and once we get past 1.5 inches, I'll allow it to go up to a full 100% of specified velocity. Depending on which lane we're backing into, either the far lane or the near lane, we would go either greater than 6 inches or less than 6 inches. Based on that, once we get into the area where we're, for our condition, in this case it's less than 6 inches, so if the average distance traveled is greater than 3.15 and the two photoreflective sensors are showing a 0 input, they're not seeing anything, and the average distance offset is active, we've just crossed the white line. But that is just the exact spot. As we transition off the guideline, I need to go a little bit more, and that's what this code here is doing. We're going to add another 0.15 inches of travel. I got that incorrectly stated at 0.2 inches. But that is just marking the spot where that lane was encountered, and then from here we will go the rest of the distance looking for, making sure our average distance is greater than that offset, this guy, and the average distance offset is active, meaning 1. Then we can stop the motor and update position, etc. And finally here we see that if the distance to go is less than 1.85 inches, I need to override and start slowing down so that we don't overshoot. This is our decel routine. So I just set the override value and adjust the run velocity. While we're in the code, I'm just going to point out that you will see this in the version that I provide online. The code is here. But as I'm making note, most likely this will be deprecated, so I won't waste time today going through and explaining this. Let's take a look one more time at the full maneuver from beginning of this whole plan, or this whole trip, that we just saw. And there you go, all the primary maneuvers that the Zoomy has to perform. Well, that was a lot of material to cover. I apologize it took so long. I tried to get through it as fast as I could, but I also needed to cover as many details as I could. But that should give you a little better understanding of how the Zoomy moves, what information it's using to make decisions, to perform the individual elements of each motion, acceleration, cruising, deceleration, when to stop, where to stop, all of that, as well as the feedback sensors that I am now relying on. You'll notice there was no mention of the distance sensor being used or the Hall effect sensors, either the left one or the right one. So things got a lot simpler. The logic might have got a little more tricky, but certainly overall everything was simplified with this huge rewrite during the last month or so. In the next video, I will be covering a few more changes that I made, and we'll be talking about a massive amount of tests that I've run. I won't show all that because that would take a couple of day-long video, but we'll talk about the results of it and how that will affect how the overall Zoomy experiment moves forward, or I should say the Zoomtown experiment. Thanks so much for sticking with me to the end here. I really appreciate it. Hopefully you enjoyed it, and hopefully I'll see you again in the next video.